Welcome back to the lab. Today we're going to design the power supply that's capable of stepping up 11 volts to 250 volts DC. Holy cow! We need to design this power supply because it's a critical part of our UPS project. For those just tuning in, a UPS is a piece of equipment that generates a high voltage AC waveform, just like our power company usually does, except for during a blackout. Where I live, this voltage happens to be 120 volts and 60 hertz. There are multiple ways to generate the waveform we require, but the method that we chose uses a DC supply with a higher voltage than whatever we want to output, in this case 170 volts. We did this because by implementing this architecture, we cut out around $90 of cost and 50 pounds of weight from our design, and we did this by eliminating the line frequency output transformer. When you're manufacturing thousands of devices a year, using a custom line frequency transformer may be more acceptable, but for us, working in small quantity and off-the-shelf parts, the high voltage DC bus seems to be a much cheaper option. Well, I suppose that's enough yammering on for one intro. Let's get into these details. If you haven't seen our video about designing the transformer that makes this power supply possible, you should really check that out first. You may be shocked at how easy it was to design and build. We've already walked through our calculations that are behind this transformer design, and those calculations were ultimately what led to our part selection, so we'll skip over those two steps in this video. Now you might be wondering, how does designing a transformer lead to picking switches, diodes, and controllers? Well, the controller dictates our switching frequency, which is a critical part of designing any transformer or switch mode power supply. Besides that, the transformer design will dictate how much voltage and current we need to handle on both the input and output sides of this converter. Therefore, that'll give us all the information we need to select the appropriate switches and the rectifier diodes on the output. In this case, for the switches, we selected some beefy N MOSFETs for the converter, and the output rectifier, we just put some silicon diodes out there. And the parameters we needed to make those decisions were right in front of us. All this to say that we won't be focusing in on the part selection for this video, because we already did that in the last video, so click on this card to check it out now. Today we'll dive into what makes a push-pull converter work, and some design compromises between the push-pull converter and an HBridge power converter. These are the two fundamental operating modes that we were considering. The theory, application, and controller for these two supplies are very similar, but there are a couple nuances that might lead a person to choose one over the other. So let's start our story by drawing some parallels to something that's already familiar to most of us, the humble buck converter, or in other words, the most common topology of a step-down DC to DC switch mode power supply. The push-pull and HBridge topologies are fundamentally built on the same topology, the same theory, except for the fact that they use a transformer. This means that if we used a transformer with a turns ratio of 1:1, it would be impossible to generate an output voltage greater than the input. It's important to note that isolation can be established, where with a buck that's not possible, and that's of course if we use an isolated transformer. If instead of a 1:1 ratio, our transformer ratio is a 1:23, like it is in our UPS project, that means that we're able to step up the input voltage by multiplying it with a factor of 23. Kabang! What a voltage multiplier! Now, losses within the transformer, rectification diodes, and MOSFETs will bring that ratio down just a little, but that's the theoretical maximum. We will never be able to achieve voltage multiplication with more than 23 times the input voltage, whatever that may be. A push-pull converter requires a bipolar square wave to be applied to the primary side of the transformer. Same for the H-bridge. Let's break that down. A bipolar signal is one that varies from a positive voltage to a negative voltage, and that's centered around 0 volts. A great example of this is a 120 volt sine wave supplied by the power company, which reaches a maximum positive voltage of 170 volts and a minimum voltage of negative 170 volts. That's great, but the complementary type of wave is called a unipolar signal. Unipolar signals vary from 0 to a positive or negative voltage when active. In other words, they can only be positive or negative. They can't be both. above and below ground. A great example of a unipolar signal are the digital outputs of a microcontroller, which can vary from the supply voltage to the local reference voltage, but never below the reference or above the supply. A bipolar square wave is necessary in this case because by constantly changing the direction of current through the primary winding, we are able to transfer energy through the transformer to the secondary side. And we do this twice per switching cycle. When we apply a positive voltage, it'll happen in the positive direction, and when we apply a negative voltage, it'll both reset the transformer and push some power through in the negative direction. This automatic reset prevents flux from building in the transformer over time and saturating the core. This maximizes the time that energy is transferred through the transformer as well, which reduces ripple when compared with another topology like a flyback converter. This action also increases the power density of the switch mode power supply overall by leveraging both halves of the switching cycle to push power through. Okay, great. So we need a bipolar square wave to be applied to the primary winding of our transformer. But how do we actually generate that? I mean, the voltage applied to our system is unipolar. It comes from a battery or a single DC power supply. How are we going to generate both a positive and a negative voltage with respect to our primary winding? Well, to complicate matters further, not only do we need a bipolar signal, which contains both positive and negative voltage, and need to generate that from a single-ended supply, but this square wave also needs to have a lot of oomph behind it. Now that's a technical term. In our case, this square wave will have an amplitude of up to 40 volts 0 to peak, and currents up to 50 amps. This is all at a frequency of 100 kilohertz. So, in all fairness, we haven't run the formal calculations yet, but I am pretty confident that that 40 volt 50 amp signal isn't coming out of a control circuit directly. We'll need some sort of intermediate circuit capable of handling the full output power that'll translate our control signal, our logical control signal, into a high power version. This high power copy of our control signal must be capable of sourcing a lot of current without being distorted. And that's what I mean by handle the full output power. When that happens, the converter should work as expected. One of the output stages we can use is an HBridge paired with a single primary winding. This is the HBridge converter. And it uses an HBridge to apply both positive or negative voltages across the primary winding by alternating which terminal is connected to the positive voltage and which terminal is connected to ground. Only 2 switches are ever on out of the 4 at a single time, but all 4 switching elements must be capable of handling the full voltage applied at the input and the full current through it. The current flows through a high side switch, through the winding, to ground, so 2 times the series resistance of the FET. This has one big disadvantage. This design requires a high side gate driver, and that'll limit how much gate capacitance our high side FETs can have. If there's too much gate capacitance, these FETs will turn on slowly, and our design will be really inefficient. Limiting the gate capacitance of the high side switches will probably demand that we select a more expensive part, and this will lead to either more losses in the switching MOSFETs if we ignore this factor due to slower switching times. Despite this characteristic, HBridge power conversion is a great way to architect a switch mode power supply capable of moving some serious power. But I'm not sure this is the best choice for our switch mode power supply because we have a lot of input current and relatively small input voltages. Which brings us to our second method, well, a second method of generating a square wave. And this one uses a pretty clever trick in my opinion. This is the push-pull converter. A push-pull converter uses 2 primary windings, but these are wound in opposite directions. Oh boy, that's hard to do. In this case, the physical construction of the primary winding is how we invert the polarity of the applied voltage. Even better than the HBridge, this polarity inversion occurs without actually needing a negative voltage present in the system. To say this in a different way, switching one half of our primary to ground generates magnetic flux through the core in what we'll call the positive direction. Turning that off and switching the other side of the primary to ground generates magnetic flux in the opposite direction. This might seem a little far-fetched or difficult to understand, but how can I be so sure? Well, the right-hand rule is something that we learned in university to visualize the winding direction, to visualize how the winding direction of a transformer affects the direction of magnetic flux flow. Send the current with the same polarity, but wound in the opposite direction around the core, and our flux will have the opposite direction. This is guaranteed to invert the direction of our flux, even though current's technically still flowing from VCC to ground in both cases. While it's a little more difficult to visualize because you have to think about fields and flux and all that sort of stuff, it has the same effect on the output of our transformer as the truly inverting voltage present in the HBridge converter. Not only do we achieve the exact same effect, but we do this while only using 2 low-side switches, or switches to ground. This eliminates our concern about having maximum gate capacitance limits on high-side MOSFETs, which could save us some serious money. Not only can we select cheaper FETs and a cheaper controller, we've also eliminated 2 of the 4 required switches. This will save us even more money in silicon, but some of that cost will move to the transformer. We've halved the number of switches required and reduced the cost of our FETs, but doubled the quantity of primary windings. Nothing comes for free. Requiring 2 primary windings means that we'll be using twice as much copper in the primary winding if we want to achieve the same efficiency. Well, this is because both primaries need to have the same resistance if they're handling the same input current if we want it to dissipate the same amount of power. This is because the push-pull topology, even though it has 2 primary windings, only passes current through one of them at a time. When compared to the HBridge converter, you're flipping the voltage with the FETs, so you have more losses in the FETs, but you can use less copper. This is a less than ideal effect of the opposite wound windings, but the biggest negative impact of the push-pull converter is the fact that when one primary winding is switched to ground, the other side will have twice the input voltage applied. When we're working with small input voltages like 11 or 40 volts on the input, it's pretty easy to find a FET rated for 80 or 24 volts. But if you're working with 100 volts on your primary side, something like the push-pull converter might be completely written off just because you'd need such expensive FETs to handle that series voltage. Like we said, not a huge impact for our system, but something to consider in your own designs. With the topology selected, let's take a moment to dive into LTspice. I've got an example set up for us that uses ideal voltage sources and ideal switches, and this will generate an ideal control signal right into the inductor, or the transformer, with a fixed frequency and fixed duty cycle. We'll use this model to discuss the way that power is flowing through the push-pull converter, and hopefully cement everything we just learned about push-pull topologies. Getting our bearings in this simulation, you can see the 2 low-side switches, power supply, control signals, and the secondary side winding. We have capacitively coupled the secondary side to ground, and this is so that the isolated reference potential is at least loosely tied back to ground. That just makes the plots work better in LTspice. So let's begin this investigation with the control signals. The duty cycle of the converter is immediately obvious by inspection. The off time is when neither control signal is active, and the on time is when either control system is active. In this example, the duty cycle is fixed to 80%. This is a little different than the buck topology since there are 2 sets of control signals, but this isn't completely new either. These control signals look a lot like a buck converter with synchronous rectification, except for the whole high side FET and transformer business. Let's focus on the A side switch and the L1 half of the primary winding for now. It appears that whenever the A signal is active, there's 12 volts applied across this L1 half of the primary winding. When the A signal is inactive, there's negative 12 volts across L1, and this is due to that effective negative 1-to-1 turns ratio between the 2 halves of the primary winding due to the opposite construction. The negative voltage applied across L1 suggests that we were correct about applying 2 times the maximum voltage across the low side switches. Let's verify that for sure by plotting the voltage across S1. Ringing aside, we can clearly see that approximately twice the input voltage, which is 12 right now, is applied across S1 when Control A is disabled. Sweet! No surprises. The higher voltage applied to this low side switch is, again, both expected and a fundamental trade-off about how using the center tap primary winding to achieve bidirectional current flow happens. I know that sometimes an engineer can only see what they want to see, so let's not completely ignore the massive transient voltage events aligned to when S1 and S2 are switching. It appears that the inductances in this circuit are causing high voltages for a very brief amount of time. 400 volts is pretty unrealistic in my opinion, but we'll probably see somewhere on the order of 15 to 20 volts in our real implementation. And the reason why it'll be so much lower is because there's a lot of parasitic elements in the real world that will help to crush these transient voltage spikes. Not only will our switches be turning on and off slower, there'll also be some capacitance from every trace of the PCB to ground. In our case, there's a lot of plane shapes for these nets, and those will provide a non-negligible quantity of parallel plate capacitance just in the physical PCB itself. So because of that, the transient voltage spikes will be attenuated, but they won't just magically disappear. So we do need to build some margin into our MOSFET drain to source voltage rating to accommodate this. We should also spend some time thinking about how fast we should really be switching our windings on and off, and seriously consider adding a snubber and or a Zener diode across our MOSFETs to prevent damage. Just like we did in the simulation. Displaying both the A and B control signals on top of the voltage applied to both inductors, this can show us that a differential square wave is truly being applied across the primary windings. And again, we're achieving this by alternately switching both of our primary windings to ground. This bipolar signal has a zero to peak amplitude equal to the input voltage, which is awesome because that means that we've just confirmed that this push-pull switch mode power supply is effectively performing the exact same action as the full HBridge power converter. Not to mention we've done it only using 2 switches. Now that's great news all around, since we've probably just significantly reduced the switching losses in our converter. Rather than needing to pull all of the current through both a high and low side switch, only one switch will be in series with the transformer winding at a time. This will significantly reduce losses, and this will lead to a higher total UPS efficiency. Higher efficiency means cheaper components, less heat generated, and a longer runtime for the same battery capacity. Now before we get too excited, let's take this party over to the secondary side of the power supply to make sure it's coming out right. Looking at voltage across the secondary first, there's definitely a square wave coming across the transformer. Adding the control signals to this picture, we can clearly see that the square wave is aligned to the rising edges of the A and B control signals. Displaying current through the secondary winding shows us a waveform of equal shape and magnitude in both the positive and negative halves of the square wave. The current is building in the secondary winding while either control system is active, and it'll fall off quickly to 0 during the dead time of the power supply. This is what I meant when explaining that transformers don't store energy in that transformer building video. Applying power on the primary side of the transformer causes it to transfer without being stored. If this transformer were functioning as coupled inductors, like in the Flyback converter, power and current would be pulled out of the secondary winding during the dead time of the primary, and that is not the case here because our transformer is acting as a transformer. No energy is stored in the ideal case. To convert the bipolar square wave back into DC, we'll use a full bridge rectifier. We need to ensure that this rectification can handle the full output current of this DC to DC converter. It's not a big challenge for our specific UPS design since we're multiplying voltage and therefore dividing current by a factor of 23. With a voltage ratio like that, we can be confident that the output currents must be reasonable. Even if the output power of 700 watts was applied as 70 amps and 10 volts, dividing by 23 gives a relatively tame output current of only 3 amps. This is well within the capability of diode rectification for high efficiency converters, especially since we're working with such large output voltages. If the output voltage of your converter is lower than ours and your output current is higher, you'll probably want to consider active or synchronous rectification. Speaking of output voltage, let's look at how much voltage is applied across our rectification diodes, and this will make sure that we've rated our diodes correctly. These parts were originally suggested based off of the ideal worst case scenario, but maybe we missed something. The output voltage of the secondary side winding has an amplitude of 200 volts peak to peak with a 12 volt input, and the 80% duty cycle. Since we're using a full bridge rectifier, only the positive or negative half of this is ever going to be applied across one diode. We can verify this easily in the simulation. Therefore, the diodes must only be rated for withstanding the output voltage of our power supply at a minimum. Our push-pull converter has a wide input voltage range varying from 11 volts to 40. In order to make sure our sine wave will always be possible at the lowest input voltage, we made a transformer with a large turn ratio. In this case, 23. That's great, but it means that the maximum possible voltage generated by this converter could be pretty huge when 40 volts is applied. To ensure that the output rectifier diodes won't break down during a malfunction of our power supply, at a minimum input voltage, let's consider the worst case scenario, 23 times voltage multiplication of our maximum input voltage, which is 40 volts. If we run the numbers, this results in an output voltage of nearly a kilovolt, 920 volts to be exact. We'd never really expect the converter to be operating here, since our nominal output voltage is 250 volts and things would start to break around 350, but it's possible for our power supply to generate this voltage. Therefore, I decided to select diodes rated for 1 kilovolt in case we go a little crazy with the voltage feedback network. As a final exercise, let's view the output voltage, which is still climbing towards its final value. We've reached approximately 180 volts, just shy of the expected ideal output voltage of 220. This difference is due to a light load resistor that we've added to the converter to keep the waveforms looking normal. Otherwise, the ringing and transient events end up skewing the output. This inaccuracy is due to the fixed duty cycle operation. You know what this reminds me of? Man, it's right on the top of my tongue. Closed loop coffee? No, that's not right. Closed loop control. Right. Closed loop control would be capable of fixing this output voltage error. All we need in order to establish output voltage regulation is a mechanism for measuring output voltage and a mechanism for comparing that to a reference and adjusting the output duty cycle. Great! So now all we have to do is feed the output voltage back into some sort of switch mode power supply controller, which is running a control loop. If only there were some kind of standard component type dedicated to this function. You know, some kind of IC, an integrated circuit, I suppose. An IC dedicated to controlling power systems, power converters, power modules. Dang, I'm really drawing a blank here. Well, guess we're never going to build this power supply after all. Thanks for watching. Wait a minute. I've got it. A power module IC that implements a PWM controller. Ah, I knew there had to be something. We used the TL594 PWM controller, which features a push-pull control mode with open collector outputs. We feed these open collector outputs through a low-side gate driver IC to drive our FETs. This provides a large and symmetrical gate drive current in both directions, which leads to symmetrical rise and fall times. We'll talk about this more in a future video. There's only one more issue that we need to settle out. That's isolation. The switch mode power supply controller lives on the low voltage side of our isolation boundary. This is because the FETs being controlled and the digital signals hooking up to the controller, those both exist on the user side of our isolation boundary. This provides a big problem. How are we supposed to measure the output voltage without connecting anything galvanically between the high voltage DC area and the user facing area? We can't use a resistor divider. How can we establish isolated voltage feedback? Thankfully, this isn't a new problem and people have been working on a solution for a very long time. To get this analog information across the isolation boundary, we'll use what's effectively an isolated op-amp. This component translates analog information across the isolation boundary and then reconstructs it as a differential signal on the low voltage side. After routing this signal across our board as a differential pair to reduce coupling, we'll turn it back into a single-ended signal as close to the controller IC as possible, and this is to minimize the potential of noise from around the board coupling into the signal in a meaningful way. This gives the TL594 exactly the information it needs to control our output voltage effectively, without compromising the isolation that we've established to prevent electrocuting people. In case there's a high voltage fault on this DC bus, we don't need to worry about that getting out to the user control panel or the batteries. Our high voltage DC to DC converter is designed. What did it take? A custom transformer, an off-the-shelf controller, an isolated analog amplifier, a little bit of math, and careful component selection. We architected this power supply while leveraging a transformer that we designed a couple weeks back. We just finished this off by verifying that the converter will function as we expect in LTspice. Do you think that we missed something? If so, stick around for a few weeks because we'll be building up our UPS and running this power supply through its paces. With the heart of our UPS designed, we're ready to keep this design moving forward. So subscribe to be notified of our future videos where we will discuss thermodynamics for electronic components and design the DC bus crossover circuit. I think that medium power, high voltage power supplies are great. If you can't wait to get this board on the bench and see what this converter can really do, let me know by hitting the like button on this video, hitting us up on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EEforEveryone, and thank you for staying till the end. Bye! Oh, before we go, there's actually one more thing I'd like